Hello everyone, and welcome back. So we're going to continue this week's examples by continuing to work with data coming from spreadsheets, except this time we're also going to be talking about working with geographic data, so data rows that contain a latitude and longitude information. So let's dive right in. Okay, so back on Glitch, what I've done is I've remixed the blank sketch just so we have a blank canvas to work from. And so first we're going to do something very similar to what we did in the previous example. We're going to bring in data from an external spreadsheet. So I have some spreadsheets here. We're going to use this spreadsheet over here. Now, this data comes from this website over here, the National Centers for Environmental Information. And this is simply a data set that contains the world's coastlines as individual points. Okay? I chose this data for this example just because it's kind of neutral and it's going to allow us to really quickly see the results of working with our latitude, longitude coordinates because we're going to create a shape that we can all recognize, which is the world map. So this is the data we have to work with. It's simply a big giant spreadsheet that has two columns. Okay? And you could imagine a more meaningful data set might have, locations and then some other data points associated with those as other columns. This is literally just an outline of the world's coastlines. Okay? So the first column is labeled long for longitude, and the second column is labeled lat for latitude. And it's quite a big data set, right? It has a lot of points in it. In fact, it has 59,768 points. I also chose this just to show that we can work with fairly large data sets in this format. In fact, the previous example, right, was extremely trivial. We had just a few rows of data, but where things start to become a little bit more interesting, at least working in the world of P5, is when we try to work with data sets that are larger, that have a little bit more information to work with. So this is just an arbitrarily large data set as well. Okay, so just for the previous, like with the previous one, we are going to make sure this is published to the web. Okay, so we're going to grab only the first sheet and we're going to publish it as a CSV file, and then we're going to grab this link, copy and paste it, and bring this into our sketch. And let's make two variables. We're going to create a variable called coast table, and we're going to create a variable called coast URL. And then in the preload function, we are going to create the coast table object by using the load table function. We're going to pass it the coast URL. We are going to say this is a CSV file, and this file has headers. Right? Remember, the header just means the first row of the data is just the name of the columns. Semicolon over here. All right. So this one might take a little bit longer to load. Oh, it won't load if I don't provide the URL here in the variable. Okay. All right, so we can see it's a little bit longer to load than the previous one, just simply because it's a much bigger data set. All right, let's set a background color here so we don't have to stare at this white screen. It's a little blinding. Okay, perfect. All right. So for this example, because it's really like a static data set, instead of drawing it in draw, we're going to draw our data in setup, and then when we're done, we're simply going to call it no loop. And what this is going to do is just going to prevent draw from repeating. It's going to basically draw a static frame into our canvas. I could also do it in draw and have it draw over and over, but just to show you that if you want to, let's say you have a really big data set, you want to draw it, and it takes a while to draw, you can draw inside setup and then call no loop to kind of stop the interaction and the main drawing loop from repeating. So once we have a table, right, we said the way that we access each element from the table is to iterate over the rows of that table. And we're always going to do this using a for loop. So the number of rows called get row count. And so this value here is returning 59,000 and change. Okay? And then inside that table, I like to grab the row as a separate variable, just so I can only have to do this once. So we're going to get the row indicated by index I. Now this row, right, contains a latitude value. So we'll say row.get number latitude, and it contains a longitude value. All right, and as a quick little refresh here, I mean, we can scan through the numbers. We can see that longitude, latitude, right? We have some negative numbers, we have some positive numbers. So what are these values? What do they represent? Well, they represent angles, right? So the latitude is angles from minus 90 to 90 degrees, right? And this is up and down on the map. And then the longitude goes from minus 180 to 180 degrees. And this is kind of taking us around the globe, or left to right on the map. Okay? So as a first pass, we could try to represent this data visually here using a kind of a naive approach. We could use map. Okay, so let's try to see if we could stretch these values to fill, use all the points to fill our canvas. So let's calculate an x value. So the x value is going to be the longitude. Okay, so we're going to map the longitude. So we said this goes in our data set, should go from minus 80 to 180. Those are the range of values acceptable for a longitude. Let's map this to 0 to width. Okay? And then we'll do the same thing with y, except this time we're going to map the latitude. So this goes from minus 90 to 90. Let's map it from a range that's going to go between 0 and height. And then let's make sure we have a white stroke. Then we're going to draw a little point at x, y. And then we should see something that looks like the world's coastlines. And those of you who are very observant may notice it's upside down. Okay, so that's very easily fixed. In fact, yeah, the North Pole would be at 90 degrees and South Pole would be at minus 90. So let's just reverse these. Okay? So this is a very crude way of approaching converting latitude, longitude to pixels. Okay, we can simply map them. This is mapping our map to a little confusing here, to literally use whatever size of window we have. Okay, so if I make this window bigger and hit refresh, you know, this is going to change the ratio as well. This might be one example where it might be helpful because we have limited space here. Just for simplicity, instead of filling the window width and the window height, I'm going to set a fixed size for my canvas. Let's say 600 by 400, just to demonstrate here. Great. So I don't want to necessarily have to use the entire space available. Okay, just so we have something that's a little bit more map shaped. Okay, and while we're at it, we could also set this background to something that's not white. Let's go do that real quick. Let's make it 0. No. That should work. Let's try a color name. There we go. Okay. Anyways, don't need that parenthesis here. Perfect. So just so it's not as distracting. Okay. So back to our sketch here. So so like I said, this is a little crude way of mapping the coordinates to pixels, and the reason for that is because coordinates, right, they're meant to be on a globe. They're meant to be on a sphere, like our planet, unless you subscribe to the flat Earth theory, and then I cannot help you. So usually what happens when we have latitude and longitudes is we need to use something slightly more sophisticated to go from those spherical coordinates to two-dimensional coordinates, and that process is called a projection. There's a lot of different ways of projecting coordinates into the 2D space, but one of the most common ones anyways is the mercator projection. Okay? So let's see if we could calculate, actually we'll do that as a function after. So let's call this the naive map. Okay. So instead of this, we're going to calculate something called the mercator projection. And don't worry, we're not going to go over the math in a great deal of detail here. We're just going to implement it. But you'll see that the formula is a little bit more elaborate than simply just using a basic map. Okay. So in a mercator projection, the x coordinate, right, we're going to get from we're going to take the longitude, we're going to shift it over here, and what we're trying to get here is just only positive values. So the 0 point is going to be somewhere over here, I believe. And we're going to multiply that by the width of our map, which is in this case the width of our window, and 360 degrees. And for the y value, things get a little bit more complicated. So first we're going to convert our latitude into radians. So those of you who don't remember, degrees, right, are between 0 and 360, and then radians are just another unit of degrees, except they go from 0 to 2 pi for a full circle. Then we're going to calculate this mercator number, and that one we won't get into details. We take the logarithm of the tangent of pi divided by 4 plus our latitude divided by 2. And then from there we can calculate our y coordinate. And if you're looking at this and going like, what is this? Don't worry. I'm more or less with you there. We'll take the map width times this mercator number that we calculated. And I didn't come up with this equation. I researched it. There's many standard projections that are used for maps, and this is just one implementation in JavaScript. Okay? And that's going to give us an x and a y value that we can use as a point. Okay? And we don't have map height, we have height here. Okay. Turns out the 0 point was in fact over here. So you can see in this version of the map, things look a little bit nicer, right? The way that the map was unfolded, this connecting over here, it looks a little bit more flat, right? So if we compare this to the version where we have this naive mapping, the map is all kind of squished up, right? We can see that this is very squishy. In this version, it looks like things are a little bit more even and flat. So this is the proportions that we're used to see anyways when we look at world maps. So this can be useful information because even though in this example we're drawing the coastline, if you find, let's say, an image of a map online, and if you know the boundaries in angles, right, and if you also know the type of projection, which a lot of them are mercator, spherical projections, then you could use that information to plot data that's based on coordinates onto an existing image of a map as well. So just to wrap up this example, we're going to go one step further here, and we're going to convert this transformation into a function, a reusable function that we can use either in this project or in future projects. And this is also a bit of an excuse to just kind of recap how we write functions as well. So we're going to take this idea of taking a latitude, longitude, right, and transferring that into converting that into pixel coordinates, and we're going to kind of package this as a function. So let's call this function geo for geographic coordinates to xy for x and y values. And the parameters to the function are going to be the latitude, longitude that we want to convert. And then in the code we have here, we're just using the width of the window to decide like how these get mapped. But it might be, you can imagine a scenario where we might want to provide a different width and height for this visual representation. So having the ability to specify this when we do the conversion, I think would be useful. So let's add the width and height of our map to the parameters. And let's comment this out for now. And I'm going to bring this code that we wrote already and then just bring it into this function. Okay. And the only thing I'm going to change is I'm going to replace width here with map width. I'm going to replace width with map width, the parameter, and I'm going to replace height with map height. Okay. So now if we give this function a latitude, longitude, a map width, and a map height, it will calculate an x and a y value. Okay. And now it needs to return these values. Okay. Now this is an interesting little challenge because normally we've written, or so far anyways, if you followed my intro course and some of my other examples, we've only ever returned values that had, a single number. We could return x here, or we could return y. Okay, but how do we return both together? And this is where the object notation can come to the rescue here. And just to make it very clear here, I'm going to rename this variable. Instead of x, I'm going to call it the x and the y, and you'll see why in a second. Just so we don't get confused, we could make it work if it was called x, but it's going to be a little bit more confusing. So what we're going to do here is we're going to define an object on the fly. We're going to use the curly brackets to do that. And we're going to return an object as the answer that comes out of that function. And that object is going to have two parameters on it. It's going to have an x parameter, and the value of that parameter will be the x. And then it's going to have a y parameter, and the value of that parameter will be the y. Okay. So this is a nice little bit of syntax we can use in JavaScript. We could write it in one line, but we could also write this over multiple lines to make it a little bit more clear. So this this kind of shows a little more that we're returning an object that's going to have two parameters. Okay? This is very similar to when we declared our own classes in the example last week. We created internal properties of objects using the this keyword. Well, this is basically an object without any functions, just with variables inside of it. And it's going to have an x variable and a y variable. And this is setting the value of those variables. Okay? So you can see why I renamed these variables. I could have said x colon x, y colon y. That would have worked just fine, but I think it looks a little bit more confusing that way. So now this function returns an object that's going to have two attributes. So let's see how this works in our code. So we're going to call the function, we're going to say geo2xy, the thing we just invented down here, and we're going to pass the parameters that it wants. It wants the latitude, the longitude, and width. We'll use width and height as the dimensions for a map, but we can also demonstrate afterwards we can put different values over here. So this function is going to return a value out there, which means we have to catch it, and we have to put it into a variable. So let's call this variable p for point. Okay? So now this variable p has an x and a y property to it. So we can now say p.x and p.y. And there we go, our map is back over here. Just to demonstrate, we could put in different values for the map. Instead we could say 200 and 300. This just maps the coordinates into a smaller area, even though our sketch is a little bit bigger here. Or we could use the width and height of our sketch as well. Cool. So the new little bit of code that we've seen here is creating an object on the fly with some fields, some properties, and this can be really useful when you're writing a function that has to return multiple values at once. So here we want to return a coordinate, so we're going to bundle this information as an object that has an x and a y field to it. So now the thing getting returned is a coordinate. We call it p over here, and p as an x and p as a y, and they're coming from over there. So we could, I'm going to leave the naive map version as a comment here for reference. Yeah, so this is a quick little example of doing projection, which is taking coordinates, right, latitude, longitude, and then projecting them, kind of unwrapping the globe onto a 2D surface. And like I mentioned, there's a ton of different ways of doing these projections that have different attributes that emphasize, different geographic properties. This is not something I'm super familiar with, but this mercator one tends to be a common one because it gives us kind of this flat looking version of the globe. Okay. And just to repeat as well, in case it's not clear, this map here, right, is being drawn by 69,000 individual points. Those points come from our spreadsheet that is over here on Google Sheets, our coastline spreadsheet, where each row of the spreadsheet is the latitude, longitude coordinate for one of these points in here. Okay. So we'll leave it at that for this example. I'm going to do one more this week where we're going to take this idea of latitude, longitude, and just for fun, we're going to represent it in 3D space, kind of in its natural environment. These coordinates where we won't have to project them because they represent coordinates around a sphere. So let's draw this coastline as a sphere. We'll do that in the next video.